Now if I want the range, max range, I'm supposed to fly at what speed?
Minimum drag speed.
So when you have to add something to this happens only in nil wind condition.
Nil wind condition.
If it is headwind, you have to fly faster than this, tailwind slower than this, and flaps and stuff you can see. So as far as for a given flap configuration, for a given weight and stuff, this is practical only in nil wind condition, which means practically it's not possible because you'll have some amount of wind anyway, right? So in nil wind conditions, for maximum range, you fly at minimum drag speed, right? Alright. Now, say for example, if an aircraft is flying at say 10,000 feet, and another aircraft is flying at 5,000 feet. What speed is this minimum drag speed? So you know about all different speeds now, true airspeed, indicator airspeed, your ground speed. What speed is this? When you say that I want to fly at minimum drag speed, so as a pilot, if I want to fly that speed, that has to be?
Indicator.
That's right, it has to be an indicator airspeed. There's no point in giving me a true airspeed because there's nothing in front of me telling me what the true airspeed is, right? So, if I am at 5,000 feet and 10,000 feet, say for example, what is the minimum drag speed required? So say for example, the minimum drag speed in general is say 50 knots. Just example. So I'm keeping that 50 knots here. I fly at 50 knots, I'll get minimum drag, maximum range, right? Indicated airspeed is again same here, 50 knots. I'll get minimum range, maximum, minimum drag, maximum range. Now what is the difference here in true airspeed? For the same indicated airspeed.
It will be more at 10,000 feet.
That's right. So in general, you can see at 5,000 feet, if indicator is 50, true has to be 60. True has to be more. This is going to be same only at sea level under ISA conditions, right? Now at 10,000 feet, what is going to happen to true airspeed? Since the air is thinner, how can I attain this? Naturally, you know that the TAS increases at high, as you go up because the resistance is less of the air, but sometimes you have to increase the true airspeed from 60 to 80. How will you increase true airspeed? What controls TAS in the cockpit?
Your throttle?
Your throttle. So we have angle of attack which controls your attitude, and your true airspeed is controlled by your throttle. And half rho v square has that v which is true airspeed, right? So what happens is I kind of increase my throttle position, say from here to say here, right? Now think about me flying at 20,000 feet for a minimum drag speed of 50 knots. So weight, and we assume that weight, everything is the same. What is going to be the TAS?
It will be furthermore.
It will be higher. I'll keep it 120. And how will I attain from 80 to 120?
By again increasing your throttle.
This is for 60, this is for 80, this is for 120. Alright, now again let me climb, or let me just, if I again climb further up, what happens? I'll have to again increase the throttle, right? Now imagine that this is a stop, forward stop, which means I cannot advance my throttle any further forward because there's a limit always, you cannot keep increasing it, right? Now what does that, what kind of a limitation is that going to give you?
Limitation, sir, means?
What is the problem with that?
Speed limitation, velocity.
So basically, can I fly any above 20,000? I can fly, but will I be able to get maximum range?
No, sir.
No. Because to get maximum range, I have to keep up with 50. And for that, I have to increase my TAS because I'm going up.
Yeah.
I cannot increase my TAS any further because I've already reached the forward limit.
Yes, sir.
This is what is called as a full throttle height. The height at which your throttle is at full. Right? This height is this 20,000 feet as of now is called as a full throttle.
In the real scenario.
Right, say again?
In the real scenario.
Yeah.
Okay.
Yes, the real scenario. This is, so full throttle height is that height where full throttle can barely give you the minimum drag speed. This is what is called as full throttle height. So you see how altitude determines range here. So just like you're climbing, advancing, just to stop. You can climb for any further, but that's not going to give you maximum range. You keep climbing at 25,000 feet, your range comes down. Because now you're flying at a reduced speed, which is giving you a higher drag. Because as the speed reduces, your lift-induced drag increases.
Is it to do something with the ceiling height? Or that is just
Yeah, you can think about ceiling height as well of propeller aircrafts. This is mainly for a propeller-driven aircraft.
either it is your Cessna or with your
Yes, yeah, correct. All those props, turboprops, propeller-driven aircrafts, which your training aircrafts, Cessna, your Diamonds, all those aircrafts, all propeller-driven. So for reasons which we will study later, propeller-driven aircrafts, we compare or we use power to analyze their performance. We will see why a bit later and talk about propeller dynamics later. And turbojet aircrafts, not propeller, the jet aircraft, all the 320s, all those things which you see, which work on the combustion and stuff. For all the jet aircrafts, which is turbojet, T for thrust. We analyze the performance using the thrust, not the power, right? And we have seen about the range of a turbojet aircraft in one of the navigation topics, if you remember, that, say for example, when you're climbing up, usually we climb at constant what? Indicator airspeed. I climb at 80 knots, I have to keep 80 knots on my ASI, right? So I'll be climbing at a constant indicator airspeed. What is required to maintain indicator airspeed constant like this? As you go up, the density is reducing, therefore your true airspeed has to
increase.
You have to fly faster to get more air molecules, to create dynamic pressure to make your indicator airspeed constant. That's the whole idea, right? So your true airspeed increases. What happens to range with increase in true airspeed? Let me see. What is the equation for range? Range is
Distance by fuel.
distance by time. Distance by fuel.
Distance by fuel.
Distance by fuel. Yeah. Now you see, if I divide this numerator denominator with time. Yes, Anuj, you see, distance divided by time and fuel divided by time. What is distance by time? It is the distance traveled in the air, which is the distance traveled in the air with time. What is that? That's a true airspeed.
Oh, sorry.
Right?
Okay. Yeah.
What is fuel by time?
Endurance.
Fuel by time is endurance. Endurance is time by fuel.
Consumption.
Fuel by time is the opposite of that. Is the fuel consumption. Lower the fuel consumption, higher the endurance. Yeah, it's just the opposite. Right? You can write this as 1 by fuel consumption. Right? Yes. So what can you say about range and true airspeed? As true airspeed increases on a climb, what happens to range?
It will increase. Right?
Range increases. As true airspeed increases, the range is going to increase. So you're happy. The more you climb, that's the reason. One of the reasons why aircrafts, these turbojet aircrafts, they tend to be at higher altitudes. One reason they go above all the weather, less traffic. All those reasons are there, but along with that, they get more range when they go up. Right? Now we have a catch here. You can keep going up, keep going up. What happens to TAS? Your TAS is increased. What is the effect of an increasing TAS on the drag factor of an aircraft as the true airspeed increases? We have seen this graph. There's a particular catch, a particular danger with an increasing true airspeed.
No, you will hit the stalling speed.
What speed?
No, stalling.
Stalling.
Alpha stall.
Alpha stall is hit only if your lift coefficient increases. Your lift coefficient is not increasing here. You're at a constant dynamic pressure of whatever knots. For that, the true airspeed is increasing, but density is reducing, so your dynamic pressure is constant. Not using any flaps, and the lift and no angle of attack is changing, no camber is changing, so your lift coefficient is not going to change. It's the lift coefficient graph, right? Remember, not the TAS one. So what happens as you go up at a constant indicator altitude? Your TAS is going to increase. The TAS is going to increase and increase and increase. What happens to local speed of sound?
Yeah, it will reduce and you will reach the Mach 1.
That's right. So what's the equation for local speed of sound?
That's my LSS.
Local speed of sound, which is
8.95.
right in the temperature of Kelvin. What happens as you go up to this guy here? As you go up, lapse rate, temperature drops,
Increases.
right? As temperature drops, the local speed of sound reduces. Now, as you rightly said, Mach number is TAS divided by local speed of sound. When you climb at a constant indicator airspeed, yes, you can see TAS is going to increase, while what is happening to local speed of sound? It is going to decrease. What happens to your Mach number? Your Mach number increases. We have seen three graphs for navigation under Mach meter, if you remember. One, we are flying at constant CAS, constant TAS, and constant Mach number, right? CMT, CTM, all those things, remember? Yes, so same thing here. You're climbing at a constant indicator airspeed, your Mach number increases, right? Now, commercial airlines especially are not really built to fly at Mach 1. They cannot fly at the speed of sound or supersonic speeds, right? Which means even though you are not really bothered about that at lower altitudes, as you come higher and higher, that becomes a botheration. Therefore, the airlines will now put a check on the maximum true airspeed which you can actually go on. So maximum indicator airspeed. So what happens is you start climbing at a constant indicator airspeed. After a particular point, you leave your indicator airspeed, and now you will focus on Mach number, right? So from airspeed indicator, your eye has to shift to Mach meter. So if you had flown at constant indicator airspeed, and after one particular point, you have to now fly at constant Mach number. Say for example, 0.8 is a Mach number given by an airline to a particular by a particular airline, like 0.85 or something. It means that 0.85 Mach number means your true airspeed cannot be more than 85% of local speed of sound. That's the meaning of that. It has to be always 25% less than local speed of sound. So in lower altitudes, not really bothered about Mach number because it's way lower. You're looking at constant indicator airspeed. I climb at 100 knots or 120 knots or 250 knots constant indicator airspeed. After a particular point, I'll switch my eye from airspeed indicator to Mach meter, and now I start flying at a constant Mach number. What happens when you fly at a constant Mach number? So again, you can write the equation. Mach number is equal to true airspeed divided by local speed of sound. Doesn't matter where you play with, as you climb, your local speed of sound is always going to reduce, right? For reducing local speed of sound, if I want to maintain a constant Mach number, I have to also, what should be done with the true airspeed? I want to reduce my true airspeed also. So if I don't do anything about true airspeed, with reducing local speed of sound, Mach number is going to increase. If you want to prevent Mach number from increasing, I have to reduce my true airspeed. So what you were increasing so far has to be reduced now, and you have to fly at a constant Mach number. Now, how far can you reduce the true airspeed? If I keep climbing at constant Mach number, the local speed of sound is reducing constantly, which means you have to now bring your throttle back to reduce your true airspeed. Can you keep reducing your true airspeed like that? You will reach a point, because true airspeed is, when you reach a point where if you increase your true airspeed a bit, you will hit Mach number. If you reduce your true airspeed a bit, you will stall. You understand what I'm trying to say? If you keep climbing all the way up, you will reach a space where any decrease in true airspeed is going to stall the aircraft. Any increase in true airspeed is going to hit Mach 1. This is what is called as the coffin's corner.
Coffin corner, yes sir, you told us.
If you have heard about this, yeah? It's a very thin line where aircrafts are not allowed to fly because you cannot do much. You cannot increase. If you increase, you overspeed. If you decrease, you stall. Very
Overspeed, so what will happen?
So these aircrafts are not built. They're parasitic drag. See, the moment you hit Mach 1, there's a huge amount of shockwave and drag that is going to hit the aircraft. So it is just like, as I told you before, opening the umbrella when you fly fast, when you drive faster. So much of drag. If the aircraft is not built to take so much of drag, like a Concorde or a jet or a fighter jet, it can take, but a commercial airline cannot take it. The control surfaces will start ripping off, like it start breaking because of drag. Drag is an opposing force, right? It's traveling so fast forward, and this will kind of break the control surface. The whole thing starts shivering, like you will enter to Mach tech. So many such kind of issues are there. But if you slow down, you will actually stop. So that very faint line is what is called as the coffin's corner. Coffin's corner is not a problem for us now. I just went straight there. But yes, so after a particular point, you will now fly at constant Mach number, right? Now, this particular altitude at which you change over from flying at constant indicated airspeed to flying at constant Mach number. This is what is called as optimum altitude. We have studied this in nav, you remember. This is what is called as optimum altitude. Now what happens as you keep flying? What is reducing? Your weight is reducing because you're consuming fuel as you inch through, right? So what happens when the weight reduces? The lift required reduces. So what happens is you can now fly at a higher true airspeed. Your optimum altitude is actually going to now increase. Keep increase. As you fly, you can actually go higher because your optimal altitude is actually increasing. Now what is the importance of flying exactly at optimal altitude is you get maximum range. If you fly anywhere lesser, your TAS is less. TAS is less means range is less. If you fly anywhere above, Mach drag is there, and because of this Mach number thing, and therefore your range will reduce. So if you fly at optimal altitude, you will get the maximum range. And if you want to keep that maximum range all along your flight, you have to follow the optimum altitude, and that is continuously rising all the way up. But if you keep following the optimum altitude, the aircraft is continuously climbing in an attempt to follow the optimum altitude. That is what is called as a cruise climb. Unfortunately, in India, that is not allowed, so we end up doing something called as a step climb. So what we do is we go 2000, we maintain the level until we are 2000 feet below, and then you climb 2000 feet above, and again you maintain the level until you are 2000 feet below optimal altitude, again you climb to 2000. That is mainly to cater with ATC requirements, traffic separation and stuff. They don't want an aircraft that is not at a particular level, the ever changing level throughout the flight. Understood? Okay. So many things. So you can see in case of a turbo, the propeller driven aircraft, it's the range is more determined by the full throttle height, above which the range is going to drop. This is the maximum height at which full throttle can barely give you the minimum drag speed or maximum range. This is talking about optimum altitude. So you can see optimum altitude is with respect to turbojet and full throttle height. Both are heights, altitudes talking about, right? Full throttle height is with respect to propeller driven aircrafts. Both trying to give you maximum range. Now you see how the type of engine that we use, type of engine as far as altitude is concerned determines the range. So you have to align with if you look at option Bravo, question number 143, the altitude for maximum range depends upon the type of engine. If it is propeller aircraft, that altitude is called as full throttle height. If it is a turbojet, that altitude is called as an optimum altitude. So it depends upon type of engine that dictates the.
Can you just repeat the line? I guess I missed that line.
Which one?
The one just to repeat it right now.
So in case of propeller driven aircrafts, so you see the question number 153 Bravo, the altitude for maximum range depends on type of engine used. So if you are looking at propeller driven aircraft, the altitude that can give you maximum range is the full throttle height. If it is a turbojet aircraft, that altitude is the optimum altitude. So it depends upon type of engine. It's not same for all the aircrafts. It changes.